This is chapter number 8 of HC1 book. Now we need to actually define what is work and what is energy. So first we will try to define the concept of energy, and from here we will be deriving the concept of work. In general terms, when do we say that a person is doing certain work or a person has certain energy? In general terms, we say that if a person is dancing or a person is running, then we say that they are more energetic compared to a person who is sleeping or a person who is sitting. So in physics, we will take it to a different level. We will analyze it mathematically too. In physics, a moving particle is said to have an energy, is said to have more energy than a particle at rest. It means that motion does play some role in definition of energy. So earlier we have known, and if you don't know it from early, I will tell you that the type of energy which is due to the motion of an object is known as kinetic energy. So we'll be using the concept of kinetic energy. Now kinetic energy is an energy due to the virtue of the motion of the body, and it is defined mathematically as half mv square, where m is mass and v is velocity of the body. Now, can we write this same thing as half, which is a constant, and mv, v is a vector, and again v bar. What is this? This is momentum, which we write as p. Momentum is a product of mass and velocity. So we see here that due to the velocity or due to the momentum, we have this energy, and this energy is mv square by 2. Now, if there are there is a many particle in a system. Suppose a system has these many particles, this is 1, this is 2, this is 3, this is 4, this is 5, this is 2. So how do we define the kinetic energy of this whole system? The kinetic energy of this whole system, because this is a system, then uh, kinetic energy of system is equals to kinetic energy of 1 plus kinetic energy of 2 plus, and so on, whatever kinetic energy of 5. Now we can write it as, if there are I number of particles, uh, can the I equals to 1 to n. If there are n number of particles, sorry, then it will be half mi vi square. This is mass of individual particles, and this is velocity of individual particles. This is mi dot vi bar. So the kinetic energy of the system will be the sum total of all the kinetic energies. Sum total of the kinetic energies of individual particles in the system. Now, since there is kinetic energy is a property of an object, of a moving object, we can say that under what conditions will kinetic energy increase or decrease or remain constant. So we'll be analyzing that. kinetic energy may increase, may decrease, or remain constant. Suppose what happens if no force is applied on the particle? This is a particle and no force is being applied to it. What will happen? If no force is applied to the particle, then the velocity remains constant. And if the velocity remains constant, the velocity does not change, then the kinetic energy remains constant. Since kinetic energy is a function of mass and velocity. Kinetic energy is a function of mass and velocity. The mass remains constant, the mass is not changing. So we will only be focusing on velocity. And since we are not applying any external force, no external force is being applied on this, no external force from any direction is being applied on it. So there won't be any velocity, and thus velocity will also remain constant. Under this condition, kinetic energy remains same. So we can understand now that to actually change the kinetic energy, we need to apply certain force. A force is necessary to change the kinetic energy of the particle. Now we will consider a case where suppose you say this is an object and the velocity of an object is this side in the positive x direction. And suppose a force is applied on this perpendicular. A perpendicular force is applied on it in the positive j direction, j cap. What happens to this? What happens to the object? Does the speed of the particle change here? In this condition also, when the force is applied perpendicular to the direction of velocity, here also the velocity, uh, it does not have any bearing on the velocity of the particle. The velocity remains same and thus kinetic energy remains constant. When this is certain force, this is velocity, when force vector is perpendicular to velocity vector, under those conditions, kinetic energy remains constant or same. Kinetic energy remains same. Now, after this, can we come to any understanding of how does kinetic energy actually change? So to understand, we have to understand how does an external force affect the change of the velocity of the particle in order to change its kinetic energy, either increase or decrease. We have dealt with the constant thing. It will remain constant if no external force is applied, and it will remain constant when a force is applied but perpendicular to the direction of the velocity. Now, so when does kinetic energy actually change? Now, kinetic energy changes only when the speed changes, and that happens only when the resultant force has a tangential component. Now, what do we mean by tangential component? Tangential component means, suppose this is it, and the velocity is this side, then the the resultant force, the external force which is acting, resultant force which is acting has to be at an angle. There has to be an angle. Then only we will say that it will have certain bearing on the change in velocity. So we can write when tangential force is applied, when Ft is applied, velocity changes. Velocity changes. And thus, under this condition, kinetic energy changes. right now we are not knowing if the what will be its direct bearing on increase or decrease of the velocity. Velocity is just changing. It will all depend on the angle and the angle and the magnitude of the force. So suppose let us take an example where this is the ground, this is a ground, and this is a tree. This is a tree, and a fruit, some fruit falls down. It is falling down and falls to the ground at this point. So what happens? What will be the forces? A force mg, mass of the fruit and acceleration due to gravity, is applicable downwards. So we see that it is applicable downwards, and so this is the force mg equals to force, and we also see that the direction or the velocity of the fruit is also downwards. So in this case, the direction of velocity is parallel to the direction of force. So under this condition, we know that the force of gravity is parallel to the velocity. This is the gravitational force which is acting, is parallel to the velocity. So its kinetic energy increases. Kinetic energy increases as time passes. As time passes. Time passes means the time from the point it break from the branch of the tree to the point where it reaches down. So that is it. We know from uh, the projectile and the vertical motion the chapter which we read that the velocity increases downwards if gravity is acting upon it. Now let us see a similar condition for what happens if the particle is projected upwards. What happens? Because this is the ground and the particle is projected upwards. It reaches to the point, reaches some point and then falls down again. This is what happens when we throw something upwards. Now under this condition, suppose let us say it is going upwards from here. Now what happens? Now under this condition at point A, let us say this is point A. At A, the velocity is upwards. It is moving upwards, the velocity. But force, as we know, the force of gravity is equals to mg. The force due to gravity is equals to mg. Force due to gravity, not force of gravity, pardon me, is acting downwards. It means they are opposite. The force opposite to force is opposite to velocity or direction of the motion. So under this condition, kinetic energy decreases. Now, what does it have to do? Now, what bearing does it have on our understanding? Let us recollect it once more. So we know that there is kinetic energy. Kinetic energy may increase, decrease, or remain constant. It remains constant under the condition that no resultant force is acting on it. Hence, there won't be any change in the velocity, and thus the kinetic energy remains same. However, when we apply a perpendicular force with respect to the direction of velocity, then also the kinetic energy remains constant and remains same. When we apply tangential force, when Ft is applied, then velocity changes. Under this condition, kinetic energy changes. Now we will see how either it changes, increases or decreases. Now, when the force is acting parallel to the velocity, parallel to the direction of velocity, then kinetic energy increases as time passes. And when force is acting opposite to velocity, kinetic energy decreases as time passes. So we understood how it increases, decreases, and remains constant. In this, I want to add one more thing, that we know that at the topmost point, velocity will be equals to zero. So we can understand that way also, that kinetic energy here, kinetic energy at this point A, this point B, this point C is decreasing. We can say that kinetic energy at A is more than kinetic energy at B is more than kinetic energy at C. It will have more in velocity initially, and the gravity will act on gravitation. Force of gravity will act on it, and it will reduce its velocity, and thus kinetic energy will be reducing. Now we will analyze this. Now we are saying that the kinetic energy increases or decreases with respect to time. Now what does this mean mathematically? Let us change the color of this. What do we mean this mathematically? So we see that we are discussing in terms of kinetic energy increases or decreases with time. So we can do this dk by dt. Dk is our kinetic energy, rate of change of kinetic energy. Now we can write it as d by dt of half mv square. This, then we can write it as half, mass is also out, and when we differentiate, mass is also a constant and half is also a constant, it comes out, and when we differentiate v square, it comes 2v into dv by dt. 2v into dv by dt. Now this 2 and this 2 gets cancelled. This thing can become mv dv by dt. Now we know that acceleration is dv by dt, velocity is rate of change of displacement ds by dt, and acceleration is dv by dt. So we can write it as m into a, ma, and then a different v. Now we have seen above that in order to change the kinetic energy, the force has to be tangential, ft, tangential force. The force has to be tangential, ft. Let's see ft and v, ft, v. So this is our rate of change of kinetic energy, ftv. Ft is the resultant tangential force. Now, what happens if force makes an angle theta with the velocity? Now, tangential force means that it has certain angle. What happens then? Then under that condition, we can write Ft is equals to F cos theta. Suppose this is an object. This is the x plane, and a force is applicable on it. Force is applicable on it. Force is applicable on it, making angle theta. Then we can say that the force is cos theta along negative x direction. So this is what tangential velocity is, the tangential force is. So we can write it as Ft equals to F cos theta. Then using this, this formula becomes F cos theta into V. Now, since we know that we have a cos theta here, we can write it as Fv cos theta, Fv cos theta. And we know that if there is cos theta, it is a dot product. Then we can do that F bar dot V bar. Since it is cos theta, it is a dot product. This is it. Now we will come to a different paradigm. Now we are slowly moving into understanding the concept of work. Now we will use the mathematical notion as I have told earlier. What is velocity? In terms of differentiation, it is dr by dt, where r is some distance parameter. Here I told you that velocity is distance by time. That velocity is rate of change of distance. Here I told you. So I have taken s. We will take dr here, the convention. And then this whole thing becomes f bar dot v. V is there. This whole thing becomes dr by dt. Now, what is this equivalent to? We are considering, we can write it as dk upon dt. Rate of change of kinetic energy is equals to f bar dot dr by dr upon dt. Now dt gets cancelled. So we are left with dk is equals to f bar dot dr. Now what is this? Where did we arrive? What is this? What do we mean by this? So now since this is also a dot product, f bar dot dr, because above we calculated the dot product only, we put the values in dot product. So this is also a dot product. So can we write it as f dr cos theta, f dr cos theta. Now this thing, f dr cos theta, this is known as the work done by the force on particle. Work done by force on the particle. Work done by the force on the particle for or during small displacement dr. Small displacement dr. Dr is the small displacement. This is the work done, f dr cos theta. You see how we arrived from the point of energy. First we understood that anything moving has energy. Then we quantified that in terms of mathematics. Then we tried to understand that how the force affects the external force, the resultant external force affect the change of velocity, which further affect the change in kinetic energy. Now we came to the conclusion that the rate of kinetic energy, during the calculation of rate of kinetic energy, we can arrive at the work done function mathematically. This is the work done function. So energy is very much intertwined with uh, the work done function. Now, can we, since this is a small displacement, so the work done on particle, work done on particle by force F bar, by force F bar acting for finite displacement. Now we came to the conclusion about the small displacement dr. Now we need for finite displacement. What does finite displacement mean? We have read in other chapters what finite displacement means. We have read in other chapters what finite means, what infinite means. Finite means some quantity which can be quantified, which we can count. which we can come to a conclusion. Now, suppose the particle moves from here to here. It takes some x, y, z path. Now we were calculating. Suppose the dr is the work done for a small distance. It is much smaller than this, but for understanding, let us see. For this small distance, for this, for a smaller distance, what we can do is, suppose this is 1, this is 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So what we can do is either we calculate mm, the FDR, dr cos theta for every small thing and add and sum it. Then we will come to the conclusion. But this will be very tedious. We take the help of mathematics here. We know that if we have to sum over a distance or sum over a length, sum over the path traversed, we use the concept of integration. So total work done will be is equals to integration of f bar dot dr bar. So I am explaining this very simply, I mean, from the lowest level possible so that you can build a base on which you will be able to apply these concepts. Generally, what we do is people will define energy and they will define work that force into displacement. You already know this in 9th or 10th class, we study work is equals to force into resistance. But to understand why we are using integration, why not differentiation here? What is differentiation? What is small displacement? What is finite displacement? We will have to discuss those things and think on those things. It will take some time, but it is good for building base. Now we can write it as f cos theta dr. Now this will lead us to two different statements about work. We are seeing how beautifully maths is used to define physics, and physics is used to understand the day-to-day things in English language. So now integration, inside the integration, we have both F and dr. So if F bar is the resultant force on the particle, we can say that if F bar is F resultant, then work done is equals to F bar dot dr bar, F bar dot dr bar is equals to integration of dk. Since this is all about dk, we know that dk is equals to F dr. Now, we know in integration, we are integrating it from where to where? From say at some distance from here to here. Then when we integrate from here to here, we use those points. Suppose we are using from some point 1 to some point 2, we can write it as kinetic energy at 2 minus kinetic energy at 1. We know it from integration. If you don't know integration, I have made a video on that also, or you can message me also to understand. I'll teach you basic mathematics also, but we are very far now from the basic mathematics part. You should know it by now. So using this, we can say that the work done on a particle by the resultant force is equal to the change in its kinetic energy. This is the change in kinetic energy. So we can say work done on a particle by F resultant force is equal to change in its kinetic energy. So now we understand that the how energy and work is related. Work done on particle, we write it on only. Work done on particle by force resultant force is equal to change in kinetic energy. Okay, why are we considering this resultant force? Let me briefly tell you. Suppose this is a particle and this is the force. This is the force. The force is coming from many corners, many directions. So either we will consider each and every individual work done by each and individual forces, or either we will just perform the resultant for the force, and then we will define it. The thing will come similar. We will see it in the next definition of our work. So suppose this is F1, this is F2, this is F3, this is F4, and this is F5. So a lot of forces are there, and these are individual forces. Then the resultant force, what will be the F resultant vector? F resultant vector is equals to F1 vector plus F2 vector plus F3 vector, F3 vector, and so on. So what will be the work done? Work done is integration of F bar dot dr bar. Now since we have individual forces, you know that we can sum it up. F1, F2, we saw it in this diagram, that if anything is applicable at different point, we can sum it up. Integration is nothing but summing over a large distance. We can say it in most simplest term, integration is just summing over large distances. This is F1 bar plus F2 bar and so on up to F5 bar and dr bar. We have removed this integration because we added it. Integration means adding. We are taking hold of the concept of integration, and then we are just summing it up. In the above definition, we understood it in terms of kinetic energy. Now we are understanding in terms of sum of individual forces which act on the object over the distance the object traverses. But if we have to consider individual forces, say F1, we will again use integration. F1 dot dr bar plus F2 dot dr bar. Object, we have a single object and it is traveling the same distance, same displacement. F3 dot dr bar and so on. Where this thing, integration of F1 bar dot dr bar is work done by force F1 on particle and so on. F2 is work done by force F2 on particle. Thus, based on this, we can say that work done on particle by resultant force is equals to sum of the work done by individual forces, sum of work done by individual forces. I use these mathematical notations to make you familiar with this, because most of the students also get scared in JEE Advanced due to certain specific notations which are being used. Although the question may be simple, but due to the notations, people get scared. The students get scared. So I'm making you familiar with the notations also. So we saw here that work done on particle by resultant force is change in kinetic energy. And here the work done by resultant force is equals to the sum of work done by individual forces. So we can say that done on the particle by resultant force is equals to sum of the work done by individual forces is equals to change in kinetic energy. Let me change the color. This change in kinetic energy, this thing. And here. This is an important statement. Now, the work done on a particle by individual force is not equal to the change in its kinetic energy. If we only analyze individual forces F1 dot dr, individual force F1 dot dr bar, work done by this individual unit, just work done by force 1 is equals to integration of force 1 dot dr bar. This is not equal to change in kinetic energy of the particle, because other forces are acting too, because we have F2, F3, and so on, other forces too. So it is only equivalent when we use this term sum of work done by individual forces. If the sum of work done by individual forces is there, then only it will be equivalent to the change in kinetic energy. So let us do one summation thing. We will analyze all this work done, work done on particle, by F resultant, not F individual, F resultant is equals to change in kinetic energy, which is equal to sum of work done by individual forces, or we can write it as sum of work done by Fi. Now this is the work done, and the statement that it is change of kinetic energy, this is the change in kinetic energy is equivalent to the work done on the particle. This statement, this much part, is the work energy theorem. This is the work energy theorem, nothing else. Work energy theorem, WET. So now we have analyzed energy, we have analyzed work done. Now what happens when we have seen the rate of change of kinetic energy, rate of change of kinetic energy, dk by dt, and we arrived at some thing for work done. Now we will see what is the rate of doing work done. What is the, how does work done have an effect when we do a certain work for some time. So we know that if we do some work is equals to F bar dot dr bar. Now if we do dw by dt, rate of change of work, the change in work done with respect to time, this is known as power. This thing is known as power, which is equivalent to F bar dot dr bar by dt, which is equivalent to force into. So we have to remember two formulas for power. Power is equals to work upon time. This is just for remembering. It will be dw by dt. We will understand through questions what dw means, what dt means. Those things will be clarified. But in simple terms, it is rate of doing work upon time, and it is also equal to the product of force into velocity. So the questions are asked generally based on this force into velocity thing. Now we will understand, now that we have understand energy, power, we have understood energy, which led us to understand what is work, which led us to understand what is power. So what was energy? Energy was kinetic energy. Right now we were concerned with kinetic energy. Kinetic energy is equals to half mv square. So the unit of kinetic energy was, for any unit, the unit is joule, and we can calculate it from here. It is mass. We can calculate the dimensions from here, mass and length per unit time. So length is square, time inverse square, ml square t inverse. Now for work, we know work done is equals to force into dr bar. Now this also, what is the dimension of force? Force is ml t inverse 2, and dr is length. Now is this m l square t inverse 2? Are the dimensions same for energy and work done? The dimensions are same, then the unit is also same. So the SI unit, this joule is also SI unit, SI, SI unit. Now the SI unit for work done is also joule. We know about power. Power is equals to work upon time. What is work done? Work done is SI unit is joule. So let's first understand dimensions. So the work done dimension is ml square t inverse 2 divided by time. So it is ml square t inverse cubed. Inverse cubed. So its unit is work done is joule and time is second. So it is joule per second, which is also known as, denoted by W, and known as watt, denoted by capital W, watt. So these are the SI units of energy and work done. Now to understand the questions, sometime there is also one arbitrary, one not arbitrary, one another unit for work done, which is sorry, another power unit in terms of horsepower. You must have even heard it, horsepower, which is denoted at HP. So in earlier days, we used to denote the power of any engine when the engine was invented during the earlier days. Before that, people used to travel on horses for long distances. So it was on horsepower, and later on it was quantized that 1 horsepower is equals to 746 watt. 746. We need to remember this. Questions come basis this on sometimes. Now we have understood the most basic concepts. Now we will dive deep into something which is the pure physics domain. Let us change the color. Now we will see work done by constant force. Work done by constant force. We know that work done is equals to integration of F bar dot dr bar. But if F bar is constant, then it becomes F bar dot integration of dr bar. See how beautifully we are using mathematics for physics. If F bar is constant, if we are applying a constant force, then F bar comes out of this integration, and now we have to integrate over the distance, over the length, because the force will be acting. Suppose this is the particle is moving xyz any direction, and it reaches here, point B, from A to B. And if the force has been constant throughout, the force hasn't changed, then we only need to understand the displacement of this whole thing, and we will come to the conclusion. So this is integration. For small distances, we integrate. So If we integrate, this is F bar dot R bar. Now, each and everything you need to understand the concept. Otherwise, there will be certain uh, questions, certain practical applications question which you will miss because you did not understand what dr meant or what r meant. Why am I writing r bar here? Why am I writing dr bar here? So you need to understand all of it. Dr bar means small displacement. R bar is the total displacement. R bar is R bar is total displacement. Total displacement of particle during which the work is calculated. If we calculate the work from here to here, from A to A dash, then we will calculate the total displacement for from A to A dash for whatever we are calculating the work for. Then we already know it that it will be Fr cos theta, Fr cos theta. This whole thing for constant force. If the displacement is along the force, if the displacement of the object is moved here, and force was also applicable here, is along the force, or in the case of the tree fruit falling from the tree, displacement was in this direction and force due to gravity was also in this direction. So along the force, then under that condition, theta is equals to 0. Then what happened? We know that cos 0 is equals to 1. Then work done is equals to just the product of force, just the product of Fr. Then it becomes Fr, force into R. Now we know that the force of gravity is also a constant force. The force of gravity is equals to m into g, and the mass is not changing. Neither is the acceleration due to gravity. None among these two things change. So it is a constant force. Now suppose if a particle moves from A to B along some curve, and that AB bar makes an angle theta. Now what happens if a particle moves from A to some point B, to some point B? This is A and this is B. And this displacement thing makes an angle theta with the vertical, makes an angle theta with the vertical. What happens then? Makes an angle theta with the vertical. Let us see from here. Okay, let me make this diagram again. Suppose we throw a particle from here and it reaches this point. This is point A and this is point B. And this is the angle it makes with the direction of force. We know that when we are throwing something, it is mg. The mg is acting downwards. The mg is acting downwards. Mg is acting downwards. And this mg, the force of gravity, is constant over the whole distance. It is constant because it is a function of mass and gravity, mass and acceleration due to gravity, and both these are constant. So the force is also constant. Now if the particle moves along that curve, this curve, A to B curve, and makes an angle theta with the vertical, this vertical, the work done by force of gravity, what will be the work done by force of gravity? this work done is equals to force of gravity into displacement, but that displacement will be, since this is AB and along the direction of force along the vertical, this is AB cos theta. So this becomes force of gravity is mg and AB cos theta. If this is AB and this is cos theta, suppose this is the height from which the ball was thrown. This is the height. Then this becomes mg h, where h is equals to AB cos theta. What is AB? The AB was in this direction. This is the AB and this is the angle theta. This was the height. So this becomes AB cos theta. This becomes AB cos theta. H is the height descended by the particle. If a particle ascends a height, if now the work done is, when it descends, it is mgh. Particle descends. Descends. Now, what will happen to the work done if the particle ascends? Particle ascends. Particle moves up from B to A. What will happen? The AB cos theta will remain same. Mass will remain same definitely. G will remain same. But now G is acting downwards and the ball is going upwards. So there will be negative G. Thus, the work done will become minus mgs due to the force of gravity. So if the particle goes from the point A to the point B along some other curve, the work done by the force of gravity is mgh. So the work done by constant force in going from A to B depends only on the position of A and B. We can say that the work done by a constant force, gravity force due to the gravity is a constant force. It is not changing. So it depends only on the position of A and B. Only on the position of A and B means this is the force and this is the distance. So it depends only on the position of A and B. And this H denotes about the position of A and B. So it depends that. And it does not depends on the actual path. Even if say, what do we mean by does not depend on the actual path? It does not depend on the actual path. So suppose this, we make the diagram again. This is theta. And suppose if the ball is thrown again, this is mgh, we know that. But even if the ball is thrown like this and it takes, due to something, it takes some path like this, then also due to constant force, this will still be, the displacement will still be AB, this AB, this will again be theta, and this H will again be AB cos theta. So we can very well say that it only depends, the work done by a constant force depends only on the initial and final position, the A and B, and not on the actual path taken. So if a particle starts from A and reaches the same point A after some time, the work done by the gravity during this round trip is 0. If it starts from A, reaches there, and it comes again to the point A goes to B, and again returns back to A, then the work done will be, since work done is Fr, R is displacement, and since displacement will be 0, then work done also is equals to 0. So the work done by gravity during this round trip is 0, as the height descended or ascended is 0. I mean, there is no change in final position, initial and final position. So we need to understand these properties too. We need to observe these, that what type of questions are we given constant forces or a mix of constant force and a non-constant force. What kind of force is given? We need to understand all this. Each and every point is very important for concept building. If you don't build your concept, maybe you will clear JEE mains with some marks. Maybe you will clear certain exam with some marks. But in JEE advanced, you are bound to fail, because JEE advanced will only test your competence based on your applicability of knowledge. Whatever you have learned, how you are applying it. And you can only apply when you understand these things, the intricacies, the small things. Now we will understand. We have understood the concept of constant forces, that what happens, how is the work done in a constant force. It depends on the path traveled, it depends on the distance, it depends on the initial and final point. It does not depends on whatever the path it has taken. It only depends on final and initial point. And the work done will be zero if the initial and final points coincide, that the particle has traveled whatever distance, but if it comes to its initial position, then the work done for the whole path will be zero. Now let us understand work done by spring force. Now, this is going to be interesting. Slowly we are diving deep into physics. We were doing simple things. Work done by spring force. Suppose this is wall, this is ground. This is the spring. This is the box. This is certain point A. Now here the spring is neither compressed nor elongated. One end of the spring is attached to the fixed vertical support. This is the vertical support, the wall. And the other end is attached to a block. This is the horizontal plane, the ground or the table on which it is kept. Now this is initial position. The spring is neither compressed nor elongated. So we say x equals to 0. It is in the relaxed position. No work is done, no force is acting. The force is at natural, the spring is at natural length. This is NL when x equals to 0. Now suppose when the spring force, when the certain force is applied, pardon me, certain force is applied, and this whole thing, the spring is elongated, and it reaches, now the A point is here. A point is the natural length, x equals to 0 is here, and this reaches some point. This point is x equals to x1. Now we know that the spring force is equals to minus of k into x. K is the spring constant. Spring constant we will understand in different chapters. On when we study the Young's modulus and all, we will understand how we derive this k. It is an experimental unit, and this x is the distance it travels from its mean position, and the negative means that it is a restoring force. If the force is applied this way, elongation is there, then the force tries to push it back to its natural length. If it is compressed, the force is again tries to push it back to its natural length, and it's applied opposite to the direction in which it is moving, and hence this is a restoring force. We will study more about this in simple harmonic motion. So now we know that there is a movement, the work done is F into dr, and there is a movement. And we also know that in force due to gravity, it was m into g, which was constant. But here it is, force is a function of k and x. Now k is a constant, but this x is the distance. Now this is not constant. not constant. It has some value. So this whole thing is not constant. This is not a constant force. So, and still, since there is a movement and there is a force, the work will be done. So what happens to the work done here? Work done is integration of F bar dot dr bar. Think about it. What happens? What will happen in this case, in which the object moves from some point x to x plus some small distance dx. Initial point it was x and it moved to some very small distance dx. Moved through a very small distance dx. And the force applied was kx. So this is dx. The force was applied, it got elongated, it moved from a point x, and this is small distance is dx. Then what will be the work done? We know that fdr is there. So we can write f, since it is negative to the direction in which the movement is there, we can write it as minus kx, force of spring, minus kx into distance traveled is a small distance x dx. Now this whole thing becomes integration of minus kx dx. Now we can take out k is constant, so we can take this thing out, and integration of x dx is x square by 2. Now from here we were elongating, in our actual question we were elongating from x equals to 0, that is natural length, to x equals to some distance x1, some distance x1. So if we do it from natural length to x1, from natural length to x1, this thing becomes minus k by 2 x1 square minus 0 square. Since 0 square is 0, it will just be x1 square. So, okay, let me write this. So this whole thing becomes minus half k x square, x1 square of course. Now if block moves from, if block moves from x equals to x1 to x equals to x2, what happens? We will change the limits of integration, nothing else. x1 to x2 minus kx dx, which is equivalent to minus k outside, and this is x square by 2, which is x2 x1 is equals to minus k by 2 x2 square minus x1 square. Now this becomes minus k by 2 x2 square minus into minus plus k x1 square by 2. So this total becomes k x1 square by 2 minus k x2 square by 2. Now we need to play with these things, with these equations. We need to understand what each and everything means. So if the block is moved from x1 to x2, not from 0 to, from natural length to some place, from some elongation already. Suppose this is the natural length of the block, this is the natural length of the block, and this is the spring. Now it moves from here to here, some position, this is x equals to x1, and then further moves to some position x2. Now what will be work done between these two? You have to calculate that also. Earlier we calculated x equals to 0 from x equal to 0 position. So the work done by the spring force is kx square, kx1 square by 2 minus kx2 square. See how x1 is the initial position. So kx1 square by 2 from initial position minus final position. See what effect the minus kx had. If we don't employ minus in the spring force, then it will have problems. So what happens again if the work done is that we move the spring from here, the block from here to here, and then again bring it here? Then what will the work done? We see even in the constant force, we have seen that if it reaches initial position from A to B and again reaches initial position when the displacement is 0, if the displacement is 0, then work done will be 0. So similar for spring force, the work done by the spring force will be 0 in the condition when the spring or the block reaches its position from where we were calculating the work done. And the work done during the return journey will be negative to the work done during the onward journey. I will teach you, I will tell you mathematically how this is. And the net work done by the spring force in a round trip is 0. We already know that. Now let us understand different positions of a spring. Suppose this is the wall. This is the natural length of the spring. And here the spring is compressed. And here the spring is elongated. Let us make it. Now suppose this distance is some distance x and this is some distance x2. This is elongated and this is compressed. Now in the compressed sense, it is x distance compressed and x distance elongated. This is the natural length and this is natural length means x equals to 0, x equals to 0. This is x equals to compressed, so x equals to minus x, and in this x equals to plus x, and this is elongated. Now let us understand uh, work done in different positions from going from one position to another. What happens if we go from natural position to compressed position? In this, the uh, natural position is x1 is equals to, sorry, x1 is equals to 0, and compressed position is x2 equals to minus x. Now we know that work done by spring force is equals to half k x1 square minus x2 square. We have derived that. It becomes half k x1 is 0, 0 square, 0 minus minus x square. This becomes minus half k x square. Minus half k x square. This is condition 1. What happens in condition 2? For condition 2, let us go from natural position to elongated position, that is positive x. X equals x1 is equals to 0 to x2 is equals to positive x. What will be the work done then? the work done is equals to half k x1 square minus x2 square, which is equals to half k 0 minus x square. This is equals to again minus half k x square. So what does this mean? That the energy, the work done in going from natural length to compression of same length is equals to the work done in going from natural length to the elongation of same strength. So the work done is same. Now let us consider point 3. Now suppose we start moving from elongated position towards the natural position. What is elongated position? Elongated position is x equals to positive x, and x2, that is end point, is equals to the point where it reaches is 0. What happens to the work done then? The work done by force of a spring is half a x1 square minus x2 square. So this is equal to half k x1 square is x square minus 0 square. This is half k x square. Now let us see point 4. In point 4, let us see now from compressed to natural state. We went from elongated to natural here, now compressed to natural. What is compressed? For compressed, xy is equals to minus x, x2 equals to 0, and work done is equals to half a x1 square minus x2 square is equals to half a minus x square minus 0. This is again half k x square. So what does this mean? That the work done in moving from elongated to natural position of equal length of x for x distance is equals to work done in moving from compressed state to natural state. Now let us move to point 5. Now let us move from end to end, from elongated to compressed. What is x1? X1 here is positive x since it is elongated, and x2 is equals to minus x. What will be the work done here? Work done is equals to half k x1 square minus x2 square. The formula remains same, half k. See, this may get a little bit of repetitive, it may seem boring, but you will have to bear with this because this will help you understand that what actually is work done in a spring, and you will have many questions of work done in a spring in your worksheet wherever you are studying, or the worksheet which I will give you, and also uh, it will have many questions in your advanced also questions may come. So x1 is x square minus of minus x square. Now this becomes positive x square minus x square becomes 0. So work done becomes 0. And in sixth also, from moving from compressed to elongated stress, elongated, x1 equals to minus x and x2 is equals to x, that is initial and final, and work done is same, half k x1 square minus x2 square is equals to half k x1 square is minus x square, so this becomes x square minus x square, this becomes 0 again. So the work done in moving from elongated to compressed is equals to work done in moving from compressed to elongated is equals to 0. We came to three conclusions here. We came to three conclusions here. And the work done in moving from elongated from extreme position to the natural length is equals to half kx square is equals to half kx square. The work done in moving from natural to natural to compress and from natural to elongated position is equals to minus half kx square. So either side from the natural length, if we travel same distance, then the work done remains same. This was very important. You need to go through, you need to revise this and understand that the work done in moving from natural position to compressed or natural position to elongated from the same distance from the natural length, x or minus x, the work done is same. Same distance from the extreme positions, compressed or elongated, is x and x. So the work done is same. The work done is same, the magnitude is same. However, the sign changes here. The work done from extreme position to natural position, that is elongated and compressed position to natural position, it becomes half kx square. Here it becomes minus kx square. And to move from one extreme position to another extreme position, from elongated to compressed and compressed to elongated, it becomes 0. Now there is a small thing in our book which says what happens. We have already discussed it, but since it is given in book, we will discuss. What happens when force is perpendicular to the velocity? We have seen this in circular motion. Let's suppose a bob is attached to a string and it is doing a circular motion like this. And the tension force is perpendicular at any point, it is perpendicular to the velocity. Even if it is here, this is bob, the bob will be moving this side and tension force will be acting this side. This is the center. So in the circular motion, tension force is always perpendicular to the direction of velocity. So in this case, the work done by tension force on the bob is always 0. The work done will be 0. So let us see this mathematically. So if force is perpendicular to this, then we say that work done is equal to F into dr bar. F into dr bar means we can see that F bar dot V bar dt. We can say since velocity is equals to dr by dt, we can say dr is equals to V dt. V dt. dr bar is equals to V dt. So if we use that thing here, it becomes F into V bar dt. And this thing is 0 in any small interval. For any small interval time from here to here, from here to here, it is the work done by this force is 0, because it will be FDR cos theta and cos theta, since it is 90 degree. F into R bar is equals to FR cos theta, and leave the F and R alone. It is perpendicular to this is cos 90, so this whole thing becomes 0. So work done becomes 0. So if a particle is fastened to the end of the string, just this bob, and is whirled in circular path, then the tension is perpendicular to the velocity of the particle, and the work done by tension is 0 in circular motion. So one more thing is, so suppose a man is running on a track. This is a running track. If a man is running on the track and a force is applied perpendicular, it is running straight and a force is applied perpendicular. So technically the man will have some problem biologically, but if we assume only physics, then here he will have the velocity will not change, but the direction will change. it will start going this side, this side, this side, this side, this side, this side, and then the total thing, if it is acting always perpendicular, then it will get curved. It will get curved, and the man will get curved, and finally it will be a circular motion. So that is also an intuitive thing here, an intuition which you can build upon. So we will be understanding three cases. One is when the force is perpendicular to the velocity at all times. Another is when the force is constant, and another is when the force is minus kx, not constant force, as in the case we have seen in the spring. So one case is force is perpendicular to the velocity, another case is force is constant, force is constant, and another force is not constant. We have seen all these things, we are just summarizing. If this is the case, then work done by force is equals to 0 if the force is perpendicular. So this was case 1. If force is constant, then the work done by that force is F into D into cos theta, or F into R cos theta. This is magnitudes and theta is the angle between them. So in this case, the work done work depends on initial and final position. It does not depends on the total path taken. Intermediate, whatever the path it has taken in the intermediate, it isn't concerned with that. It is only concerned with the initial and final position, as I have explained already before in the how the force of gravity acts. So the constant force, one of the constant forces, forces of gravity, and the work done in a round trip or a round trip from A to B and A to B and B to A, when the initial and final positions are same, then the work done is equals to, then work done by the force is equals to 0. These are the things. As we have seen, the work done by Fg is mg, and work done by force of gravity is equals to mg h. It only depends on the path it descends, the height it descends or ascends. It only depends on that. Now, when force is not equals to constant, then one of that example is the spring force. So in this case, the magnitude of the force from x to its natural position is half kx square, as I have already x to its natural position. Work done by force is equals to, from a natural position is equals to half k x square, and from natural position to x, work done by force is equals to minus half k x square, and from extreme to extreme, that is minus x to x or x to minus x, work done by force is equals to 0. So we can see that the work done is half minus half k x square, 0, half k x square. So the work done will always be within this boundary, half kx square to half kx square, minus half kx square to half kx square, depending on whether the force and the displacement are along the same or opposite direction. So in the spring force here, if we move from this to this, the force will be in the negative direction. If we move from natural position to the extreme position, the force will be in the negative direction. The force of a spring is a restoring force, as we have read, and it will try to bring the object back to its initial position, which is this, and hence it will be minus kx square. Now, when it moves from its extreme position to its initial position, the direction of the force is still acting to bring the object towards the center, and the distance it travels is in the same direction. So it is x square, and we have already so it is positive half x square, and we have already seen from extreme to extreme it is 0. Now there is a very small article about what is work energy theorem for a system of particles. For now we were concerned only about work energy theorem of an individual particle. Now we will see work energy theorem for a system of particles. We are looking at the work energy theorem for a system of particles. So far we have considered the work done on a single particle. We were only considered about the work done on a single particle, and we understood that the total work done on a particle equals to the change in its kinetic energy. Total work done on a particle is equals to change in its kinetic energy. Change in its kinetic energy. Now, we know that we can also say that to change the kinetic energy, we will need some work to be done. For some work to be done, we need to apply some force and give certain velocity to the particle. Now, to understand a system of particles, let us just take two particles, two charged particles, A and B. This is A, this is B, this is positive, and this is negative. We know that like charges attract each other. So there will be a certain force on A due to B, and there will be a certain force on B due to A. So we also know that there will be mutual attraction. We know that already, that the positive and negative charges attract each other. And if they attract each other, then the kinetic energy of the system will change. There will be certain change in the kinetic energy of the system. And we are not we are not applying any external force right now. And still the kinetic energy of the system changes. So suppose the magnitude will be similar. The magnitude of FAB and FBA, the magnitudes are same. However, the directions are opposite. So we can say FAB is equals to minus FBA minus FBA. FAB equals to minus FBA. Now, if FAB is equals to minus FBA, FAB is the force applied on A by B, and FB is the force applied on B by A. Now, can we write that FAB plus FBA is equals to 0? From this, we can write this. We come to this conclusion. And due to this force FAB, the A will move to certain distance, and due to this force B, the B will move certain distance. So the work done by force FAB is equals to certain positive value, is equal to certain value, may not be positive, is equals to certain value, and work done by FBA has some value. I mean, it is not equals to 0. It is not equals to 0. However, if we see the work done by resultant, work done by resultant is equals to FAB plus FBA is 0. So the work done is equals to F resultant into distance each of these travels. And since this is 0, this should be 0. However, work done by FAB plus BA, work done by F this resultant is not equals to 0. And why is it so? It should be 0, but it isn't, because the two forces are opposite in direction. The two forces are definitely opposite in direction. However, the distance it travels, if A travels this side, the same distance, and B travels same distance negative side, the distances are also opposite. So the forces are opposite, and distances are also opposite. This will be displacement, not distance. The displacement is also opposite. Thus, the work done by both the forces, thus the work done by both the forces aren't isn't zero, and work done by both the forces, work done by f of AB plus f of BA is not equals to 0, has some positive value. Displacement is also displacement and forces are opposite, and they have some positive value. So we can come to the conclusion that the total work on different particles of the system, total work done by different particles of the system by internal forces, to, by internal forces may not be equals to 0. And the change in kinetic energy of this system, the change in kinetic energy of this system is equal to work done on the system by the external as well as the internal forces, internal as well as the external forces. This is very important to understand to get an intuition about how the forces work and how the different kind of internal and external forces attract each other and work together. In this, due to the resultant, this should have been 0. However, this is not 0 because the distances are also opposite. So it will be FAB into D, FAB into D, FAB into whatever distance one has traveled, plus FBA into whatever distance they have traveled. So this will be some positive value. This will be some positive value. Since this was also opposite to the direction of this, and distance was also opposite to the direction of this, then minus minus becomes plus, and this is added. So this will have some positive value. So this takes us to the conclusion that although the resultant force may be zero, but the work done isn't always 0. So the change in kinetic energy of the system is equals to work done by force internal as well as force external.